Welcome, my name is Terry Soul, and this is Programming Chaos, a YouTube channel devoted to programming tutorials. So I do these in a variety of different languages, and they're for beginning to intermediate programmers to hone their skills doing some cool and interesting projects. For today's tutorial, I'm going to be programming in Java in the processing environment, and the project I'm doing is John Conway's Game of Life, which you can see here. It's a cellular automata. In fact, it's one of the classic cellular automatas. And a cellular automata is simply a model in which the world is divided into a grid, and then in each cell in that grid, there's a little program, an automata running that does something. In the Game of Life, what that automata is doing is looking at its neighbors and deciding whether it should be alive, a 1 or a white square, or dead, a 0 or a black square, depending on the number of neighbors that it has. And so the idea is that it's sort of simulating a very simple model of life. And the colors don't really matter. In fact, one of the things I'll recommend is playing around with the colors. You can get very interesting and beautiful patterns by fiddling with the colors. The main thing is we're thinking about a cell being alive or dead. And there are lots of variations. You can have cells with more than just 2 states. And I'll talk about those a little bit at the end. Okay, so to get started with the coding, I have over here the sort of classic boilerplate for a processing sketch, which is just a setup that creates a window, in this case of size 900 by 1000, and then a draw loop. And none of this really does anything yet. But what I want to do, of course, is create this game of life. And so the first thing that I need is the board, in a sense, or the world, if you prefer, to work with. And that's just going to be a 2-dimensional array. I could make it Booleans because we only need 2 values, 0 and 1, but I'll go ahead and make it integers. In part, that means if you want to expand it and have more than 2 states, alive or dead, it's easy to do because we already have the integers there. So let's start by creating the board. So there's our board structure, and then we need to have some variables for how big it is. And our board is a 2-dimensional array. In Java, in terms of keeping track of a board, the first value is which row you're in, and the second value is which column you're in. So if you want to think of it as a table, it's row, column, and we need to know the number of rows and the number of columns, and I'll create those again as variables that we can use throughout. There we go. And then if you look back at the intro, the cells are not just single pixel wide. We can have cells that are larger squares so we can see them more easily. And it's nice just to have a variable for that, basically the scale. How big do we want to scale up our cells? Okay, so then we have to set those variables. And basically the idea is I already have the size of the window here. So the number of rows is going to be the height of the window divided by the scale. My window is 1000 high. If I want my scale, I'll give it a value, to be, say, 5, then the number of rows that I have is that total 1000 divided by 5, where height is the height of the window. And similarly, the column count, the number of columns I have, is the width of the window divided by 5. And so now that we have the row count and the column count, I can actually define my board. There we go. And I always find working with 2-dimensional arrays a little bit confusing because the first number, as I said, is the row, which is which row you're in, and that feels like the y value because it's up and down, whereas y is normally the second index when you draw things. And when we go into the drawing, we'll have to remember to keep that straight. Rows are how high we are, columns is how far across we are. In tables, it's row first, then column, but when we draw, it's x first, then y, so it feels a little backwards. But for now, we're just worrying about the table, and I just need to fill it in. So I'll just do 2 nested loops to fill in all of the values. And so the first loop is going to go through each row, and then the second loop through each column. So there's my 2 loops, the outer one going through the rows, the inner one going through each column. And It's very helpful here to keep things straight to use, say, R for the rows and C for the columns, rather than the more typical thing, which is using, for example, I and J. So here I'm filling in the board, and again, rows first, columns second, so RC in terms of the indexes. And then I'm generating a random number the way that Java does this, or processing does this with the random function, is this is going to give me a random floating point number, a number with a decimal between 0 and 1.99 repeating. So it doesn't include 2. And then I'm going to turn that into an integer which truncates the decimal. So basically I have a number between 0 and 1.99 repeating. I throw away the decimal and I end up with a 0 or a 1. So I'm going to fill the board with random zeros or ones. So we have our board. There's not much we can do with it until we actually draw it. So let's go down to the draw function and we'll start drawing it. And for that, I'm going to use exactly the same two loops here, because I need to go through the whole table, but I'm going to use them then to just draw squares in my window. So there we go, that's the drawing, and I've done some things here that are a little tricky. I'm filling with a color which is 255 times the board value. And the board value is 0 or 1, so I'm really filling with either 0, 255 times 0, or I'm filling with 255, 0 times 1, which means I'm filling with either black or white. And then the rectangle I'm drawing, first notice that I'm putting the column first, because that's the x value, times the scale, because I want to skip over that far. Each cell is, in this case, 5 wide. That's my scale, and so if my column number is 3, I need to move over 15, and then similarly the row, how far down I want to go, times the scale, and the size of the box is equal to the scale. And I should probably erase my board at the beginning by filling it in with 0, and I don't want to border around my cells, or maybe I do, but for now I'll take the border out. So I'll just define no strokes, that none of the cells have a border. And so now I can run this. Once I get rid of the square brackets, there we go, that's the problem. And there, I filled a board with random ones and zeros, random black and white squares. And so the next step is going to be to write a routine that looks at each of these squares, counts its neighbors, and decides whether it should remain on or turn off. And so we can think of this as alive or dead, on or off, black or white, whichever one we want. So I'm going to do that in a separate function. I'll just call this function update. And this, again, is a pretty standard way of doing the coding. I know that I want to update all of those squares, so I'll just put in a dummy function for now, and then write the function next. And in this case, I'll write the function right away. Okay, so in creating the update function, the first thing we need to think about is time. In a sense, we're simulating time. We have our current board, and then we need to figure out what the board is going to look like at the next time step, the next quantum of time, if you will. And the reason we have to do it is two separate boards, the old one and then the new one, is because imagine we have a cell and we update its value in the current board, then when we go to the next cell, it's going to calculate its new value based on the new value of the old cell. So we're sort of going to have them updating asynchronously. Some will update and then the others will update based on the previous update, and it actually messes everything up. So what we need to do is make sure that they all, in a sense, simultaneously update based on the current values, but we don't have a way to do that simultaneous update. Maybe if we reprogrammed it to run on a GPU, we could do it. But in this case, we can't. And so instead, we have the current board and then we have the new board. I'll just call it a temporary board. So we do our calculations in the current board and then we store the new value in the temporary board. And then when we're done, we copy the whole temporary board into the current board and throw away the temporary board. It's just a way of sort of keeping track of things without changing our values out of order. Okay, so we need this temporary board. There we go, and it's going to be just as big as our previous board, so we'll use row count and column count here again. And then we need to start calculating the values to go into it, and we need to do that for each cell. So I'm just going to copy and paste my previous for loops from up here and use those to calculate the new values. And so what I'm going to do for now is assume that I have a function that calculates the neighbors for me. So this is a function that I'm assuming is going to calculate the number of neighbors for me based on the current row and column, and I'm going to store it in a variable neighbors that doesn't exist. So let's quick create that. And then I can update the temporary board based on the number of neighbors, even though that hasn't been calculated yet. The rules are if I have exactly 3 neighbors that are alive, I should be alive. If I have 2 neighbors that are alive, I should keep the same condition. So if I'm a live cell, I remain alive. If I'm a dead cell, I remain dead. And any other circumstances, I'm dead. So if I have too few neighbors or too many neighbors, the cell just dies. That's the most common condition. So I'm going to code that one first as sort of the default. So we sort of assume that the new state is dead, and then we adjust that depending on the number of neighbors. So there, if the number of neighbors is 3, then the new value should be live or 1. And if the number of neighbors is 2, then the new value should be whatever the old value is. So default to the new value is 0, but under some circumstances, it's going to be 1 or it's going to remain the same. There are lots of different rules that can be applied to the game of life to give you different patterns. This is the classic one, which we'll stick with for now. But simply by putting in other if conditions, we can modify what those rules are and how they work. And then the last thing we need to do in the update, now that we've taken all of the new values and put them into this temporary board, we have to copy them back into our main board. And I'll do that again by reusing the existing for loops. So there we go. This takes the temporary values and copies them back into my main board. And I can't run this yet because I don't have my count neighbors function. So let's work on that. And that is going to return the number of neighbors. So we know it's going to look like this. I'm going to have to calculate the value, the number of neighbors, and return that. There are a bunch of different ways of counting the neighbors. A little bit of it depends on some decisions we have to make. For example, does our board wrap around? So if I'm on the left edge, am I counting neighbors on the right edge, or does it have a border? I'm going to set it up to wrap around. I think that's a little more interesting, and we can see some cool patterns and sort of how they expand around the edges of the world. The other thing that we need to worry about is normally we just count the neighbors in a radius 1, but we can have different models where that radius could be bigger, that range that we're looking at. And I'm going to write the code so that we can change that easily. So the first thing I want, oddly enough, is another variable. I'll call it range for the range over which we're looking at neighbors. And I will just make that 1. But this way we could easily change that if we wanted, just like we could change the scale of our model by changing that scale variable. And then I need to know which neighbor I'm going to be looking at. So I'm going to put in 2 more variables. And those are going to be the row of the neighbor that I'm currently looking at and the column of the neighbor I'm currently looking at. And I'm getting a bunch of warnings that those variables aren't being used, which is fine. The way that I'm going to program this is by looking at what is the delta. So I know my current row and column, that's in the code, that's this RC. And I want to ask sort of what is the offset so that I can find the neighbor. And this is the way I'll do it, and it may make a little more sense once we look at it in code. So this is, I think of it as the delta row, and it goes from the negative of the range up to and including the positive of the range. So dr, my delta row, is going to go from -1 to +1. That means I'm offsetting by -1 row, up 1 row, to +1, down 1 row. But by changing the range, I could do a bigger offset and I could count more neighbors if I wanted. And then I'll do the same thing for columns. There we go, except this is the column offset. And now that I know what that delta is, now I'll calculate what the neighbor column should be. So the quick part is the neighbor column is the column plus the delta. So if I'm offset by -1, then I'm saying the neighbor that I'm looking at is one column to the left. But if I want this to wrap, I've got to add some extra code. So the first thing I'm doing is adding in the full column count. And that handles the case if I'm too far off to the left. So imagine that the column I'm interested in is the 0th column all the way to the left. If I subtract 1, I get a -1. If I add the total number of columns, that puts me back on the right minus the 1 that I'm adding in. And so that gets me back on. And then modulus works the other way. If I go too far off the board to the right, the modulus basically subtracts the board width and gives me the remainder, which puts me back on the left. So this is a nice trick for handling wrapping. You add the total width, and then you do a modulus of the total width, and we'll do the same thing for the height. And just because I did the rows first here, I'm going to put the rows first. The order doesn't really matter, except for sort of thinking about things. And I realized that I think I used the full column count here, so I'll put in column count. There we go. And so that gives me the correct neighbor location, including wrapping, and now I can use it to count the number of neighbors. And really all I have to do is say, if that neighbor is a 1, I'm going to add it to the count, and if it's a 0, I don't add it to the count, but if it's a 0, it doesn't get added anyway. So I can really just say the value that I want to return is equal to whatever the old value was, so I'll do a plus equals, value plus equals this new one, which is simply the board at that location, at the neighbor's location. So if the neighbor was a 0, I'm adding 0, which has no effect. If the neighbor was a 1, I'm adding a 1, which is exactly what I wanted. Clean this up a little bit. And so that gives me the new value, and I can simply return it. So there we go. We have our neighbor count, which we're using in our update here to count the number of neighbors. And then that allows us to update the board. So let's see it go. So there we have a fairly typical game of life. That's not quite the pattern I expect. So I think I have something a little off in my rules that I need to figure out. Okay. So as I said, this is not the pattern I expect, and it's because I've made another classic error in programming the game of life. It's good, it gives me an opportunity to point it out. The rules for the game of life involve counting up all of your neighbors. However, in my 2 for loops here, at one point, delta R and delta C are both equal to 0, which means I'm also counting the current cell. And that's why we get a lot of these very stable 2 patterns, because that shouldn't be stable, because each of these squares only has one neighbor. But if it's counting itself, then it has 2 neighbors and can remain alive. So that's the issue here, is cells are counting themselves as part of the neighbors. That's really just a different set of rules, but it's not the set of rules I want. And it's a very easy mistake to make. So in some ways, I'm glad I made it, because I can illustrate it. And to fix it, I just have to put in an if condition here. I only want to add in the neighbors if my offset, delta R and delta C, are both not 0. Or I'll do it the other way, as long as one of them is not 0, I'm allowed to do this calculation. So if delta R is not equal to 0, or delta C is not equal to 0, go ahead and add that count in. Otherwise, we'll skip over. So in the case where these are both 0, we'll skip over the count and we won't include the individual in its own count. And now we get the classic Conway's game of life. And what you can see is, as I predicted, a lot of the cells died out because it was pretty dense to begin with. What you typically see in Conway's Game of Life with the classic rules are a few different things. Look, there's a glider, so that's a structure that moves along. They were recognized fairly early as a standard sort of structure that can move. You get lots of stable structures, so a little set of 4 boxes, they all remain alive, but they don't grow. You can get lots of other stable structures. You also get blinkers, so these sort of fluctuating structures, and then interesting growth. So these sort of almost random seeming patterns of growth. And this is part of why it's called the Game of Life, because it almost seems like we've got these distributions of life that are growing, using up resources, dying out. Turns out if you look at things like gliders, you can create much more complicated structures called glider guns that shoot out gliders. You can create structures that take in gliders and actually do calculations with them. So oddly enough, in the Game of Life, it is possible to build a whole computer that instead of using ones or zeros, uses gliders or not gliders, and it can do any sort of calculation that you want, way beyond what we want to do here, but it's sort of interesting. You can maybe imagine now that we have this running, it's very easy to set up other kinds of models using other rules. A common one that I've used before, for example, is modeling forest fires. So instead of just being on or off, you could have cells that represent different amounts of growth, and then whether or not those areas are on fire, and you can have fires spread and trees regrow and so forth. So that's just one of really millions of different ways in which basically cellular automata models this notion of taking the world, dividing it into cells, and each cell has its own rule that it runs. Millions of different sets of rules, really an infinite number of sets of rules that can be developed to model an infinite number of different kinds of environments. But this is the canonical one. It's a really nice one to start with. And now that you have the code, you can modify it in all sorts of different ways. What you'll notice here is that they usually, in fact, they always settle down into some pattern. And the reason they have to settle down into some pattern, at least if we have a finite sized map, is there's only a finite number of patterns that can exist. And so they either have to repeat or not repeat. The only way that you can have sort of infinite growth is if you have an infinite world, which is a little hard to model given modern memory requirements, but still can get very interesting and cool patterns and can model all sorts of real world processes. So if I run this again, just as an example, right, the general pattern looks pretty similar. We get the same sort of growths. If you look around, you may see some gliders moving through, and then more and more stable patterns developing over time. So if you like this, like I say, an infinite number of places that you can go with this basic notion of a cellular automata, starting with just modifying the colors, and then from there you can look at modifying the basic rules. And if you look online, all sorts of different rule sets that you can use. And then from there you can go to things like, well, what if we have more than just on and off states? That gives you a whole nother set of possibilities. You can move this up into 3 dimensions, so you can create a 3-dimensional cellular automata, or you can actually go down to a 1-dimensional one where the world is just a row. That gives you all sorts of cool things to do. Infinite number of places to go. This is a good starting one. If you stumble upon or find anything particularly exciting, absolutely please link it in the comments below. Thank you.